Hello everyone, my name is Carolina and I'm a PhD student at Rutgers University. Today I'll be talking to you about private multi-group aggregation, which is joint work with Rafael de Oliveira and Naim. Private aggregation has received a lot of attention in the literature, motivated by applications to federated learning, medical studies, and general population statistic applications. And the main idea is that the server wishes to compute the sum of values held by multiple users. These values can be anything from votes by the users, they can be medical test results, or maybe gradients held by these users. The users want to collaborate with the server to compute this sum, and they are incentivized to do so. However, they worry about their privacy, meaning they want to keep their values hidden. In the literature, people have looked at methods that provide information theoretic or differential privacy guarantees for this. In many applications, users belong to different groups based on their race, age, gender, or political views, to name a few. And the server wants a finer aggregate of the population. So he wants the aggregate not over the whole population, but the aggregate for each group separately. This led us to define this variation on the traditional aggregation problem, which we call the private multi-group aggregation. In the setting we consider, in addition to holding a value v, each user belongs to a different group. For instance, user 1 in this figure has value v1 and belongs to group 1, represented here by a circle. In this figure, we show three groups represented in blue, green, and red. In general, we can have any number of groups k. We assume that the server does not know to which group each user belongs to. And so a major concern for the user is to reveal his group, because revealing his group can have serious consequences, for example, discrimination based on race or age, or even higher health insurance bills if the groupings were related to diseases, for example. So to summarize, the user knows his group and wants to keep it private. This setting that we consider appears in many applications. For example, consider primary elections, where there are two groups, Democrats and Republicans. Each user's value is a vote to his preferred candidate in his political party or group. The server's goal is to tally the votes per party and find the winning candidate in each group. Another example is vaccine trials. A medical research group wants to find the effect of a new COVID vaccine on patients with or without diabetes. Participants want to contribute their vaccine test results, or in other words, their values. However, they worry about revealing their diabetic medical condition. A third example is population polling. An agency wants to poll people per group, such as race or income bracket. And understandably, participants want to partake in these polls without disclosing their group. These are only some applications, and there could be many more. Now, to be more concrete, let me introduce our setting. There are n users that communicate with a single server. Each user I belongs to a group GI, which is one of k groups, and each user also has a value vi that is an integer between -m and m. The user knows his group and value, but the server does not. We will call the probability that a user belongs to a group G theta G, and the probability that the user has value v given that he belongs to group G, we call it PGV. So the user's group and value can be correlated. Most importantly, our goal is to design schemes that allow the server to find an estimate of values per group. So the server ends up with a vector S of estimated sums. The size of the vector is equal to the number of groups k. The scheme needs to allow the server to find the estimate under privacy constraints over the user's group. So the user's groups have to stay private. While keeping in mind the communication cost of the scheme. Our main objective is to design schemes with low communication costs between the users and the server. That is because users can have limited bandwidth and capabilities. So to summarize, for a scheme we care about three things: communication cost, utility, and privacy. Or in other words, we are interested in privacy versus utility trade-offs. We determine the communication cost by the total number of bits communicated by all the users to the server. As for utility, let S hat be the server's estimate of the true sum S. Then, to find the risk of the estimator, we look at the normalized mean square error. The normalization factor here accounts for the true aggregate S being proportional to the number of users N. The third metric we consider is privacy. And like we said before, we care about keeping the user's group private, but not necessarily his value. However, since a user's group and value can be correlated, as a consequence of hiding the group, we will have to hide the user's value as well sometimes. And to measure the privacy level guaranteed by a scheme, we will use local differential privacy. Now I would like to go into more details about the local differential privacy definition that we adopt. In any given scheme, a user is assigned a query Q and responds with an answer A. In our paper, we adapt a local differential privacy definition from the works of Dwork and Ducci et al. The answer that the user communicates to the server will be the output of a randomized mechanism that we call M. You can think of the mechanism here as the method the user employs to hide his group. The input to the mechanism is the user's group, value, and assigned query. We say the scheme is epsilon locally differentially private if for a given epsilon, the distribution of the output of the mechanism is close when you change the group. And by close here, I mean up to a factor of e to the epsilon. So here, if you look at the probability expressions before and after the inequality, we only change the group, which is the private information, as is typical in differential privacy definitions. The problem of private aggregation has been looked at from multiple privacy perspectives in the literature. Some methods, such as those described by Shi et al., provide differential privacy guarantees by adding noise directly to the user's values. And other methods, such as those presented by Bonowitz et al., do secure aggregation, which consists of using cryptographic techniques, such as Diffie-Hellman key exchange to share keys, and in turn, these keys are used to mask the user's values and provide information theoretic security in a one-time path type of scheme. The main difference between the classical setup of private and secure aggregation and our work is that 1. Traditional private aggregation does not distinguish among groups, and 2. The privacy guarantees are on the user's values. Another related problem other than private aggregation is federated submodel learning, where one or multiple servers hold several submodels, and each user wants to train a private subset of these submodels. The notion of submodels here is similar to the notion of groups in our problem. However, in federated submodel learning, a user's update depends on the submodels at the server in addition to his data. So the setting is also different. So like I said, where in the literature there are no groups, in our problem there are many groups. The user belongs to one of these groups and wants to keep his group private. And for this problem, we propose a new interactive scheme, which we call the Query and Aggregate scheme, or for short, Q&A. It is formed of 2 stages, the query stage and the aggregate stage. So the user answers an assigned query instead of just reporting a noisy answer. An important feature of our scheme is that the assigned queries are completely independent of the user's values and groups. Therefore, they can be assigned offline or as part of the scheme agreement. This allows for a reduction in communication cost. We completely characterize the scheme's performance in terms of communication cost, privacy, and utility. What is interesting is that the communication cost is independent of the number of groups. This scheme incurs a cost in utility, however, the normalized error goes to 0 as the number of users increases. In this graph on the right, we compare Q&A to a scheme we call Randomized Group. The randomized group scheme is an extension of methods in the literature, mainly randomized response, and it does not include a query stage. The randomized group scheme is represented in green and the Q&A is represented in blue. And as you can see, our Q&A scheme does well in terms of privacy versus utility in the high privacy regime, or in other words, when epsilon is small. I will revisit this graph in more detail later in this talk. To better explain the scheme, I will focus on the case of 2 groups and 2 values. So each user either belongs to group 1, represented here by a blue circle, or to group 2, represented here by a red square. And the user can have one of two values, -1 or +1. As a reminder here, the groups can be, for instance, Democrats versus Republicans, or diabetic versus non-diabetic patients. And you can think of the values here as positive or negative test results. The first step of the scheme is composed of the user mapping his group and value to one of the 4 points in this figure on the right. The x-axis corresponds to group 1, and the y-axis corresponds to group 2. For instance, the user maps to this point here if he is in group 1 and has value +1. After he has mapped his group and value, the user is assigned one of two queries, query A or query B. The query is a question to the user, and here we represent this question by a directed line. It is essentially a question about whether the user's mapping is to the left or to the right of this directed line. And as you can see, a query splits the plane in half. The user is assigned one of these two queries with equal probability, or in other words, uniformly at random and independent of his group and value. This query method is agreed upon between the server and the user. So if the user is assigned query A, he knows that it corresponds to the directed line here on the left. And both the server and the user know the user's assigned query. The user answers this query with a single bit. He tells the server whether his mapping is to the left or the right of the query or directed line question. Notice that these queries are assigned randomly and independent of the user's group and value. So in truth, they can be assigned in an offline phase, before the start of the whole process, or as part of the scheme agreement. The only constraint here is that query A and B are assigned with equal probability. So there could be two phases, an offline phase where the user is assigned one of these queries, and an online phase, where he does the mapping and sends the server an answer. Let me show you an example to make this process clearer. In this example, a user belongs to group 2 and has value +1. Therefore, he maps his answer to this point here on the y-axis corresponding to his group, group 2. Let us assume he is assigned query A. He looks at his mapping and notices that his mapping is to the left of the query. So he answers the server with left or green. If he is assigned query B, he sends the server the answer right or violet. So the user's answer is a 1-bit answer. He has essentially compressed the information about both his group and value into a single bit. Another important thing to notice here is about privacy. When we look at query A here, if the user was in group 1 and had value -1, he would have sent the server the same answer, left. This is really where the group privacy is coming from. When the server receives an answer, it corresponds to a region of two possible mappings. The server cannot determine with certainty whether the user belongs to group 1 or group 2. Now that the server received the answer, let's talk about how he interprets it. Since the server knows the user's assigned query and he knows his answer, based on this figure, he interprets this answer as a two-dimensional vector, where the first coordinate corresponds to group 1 and the second coordinate corresponds to group 2. Notice that the coordinate corresponding to the user's group will always have the correct value. So here, if the user was in group 1 and had value +1, the vector has the correct value +1 and the correct first coordinate corresponding to group 1. Now how about the second coordinate? It will have a random value +1 or -1 with equal probability, or in other words, probability half. And this follows from how the queries were designed and assigned with equal probability. Here, we show how all the possible answers are interpreted, and notice that they all have the important properties that the coordinate corresponding to the user's group has the correct value, and the other coordinate is a uniformly at random value +1 or -1. Finally, after receiving all the answers from all the users, the server sums the interpreted vectors to find the estimate S hat of the true sum S. Now, let us analyze the accuracy of this scheme and why it works by focusing on the first coordinate of the estimate, or in other words, the coordinate that corresponds to group 1. The right group always has the right value, so the true aggregate is there, but with some added noise. This noise is a random variable and corresponds to the contribution of the users who belong to group 2. The noise can be interpreted as the sum of IID random variables with bounded variance, and it converges to a zero-mean Gaussian noise. Another interpretation consists of thinking of the estimate as a random walk around the true aggregate S. The probability of stepping to the left or right is 1/2, and the number of steps of this random walk is proportional to the number of users in group 2. To summarize, we introduced an interactive query and aggregate scheme. In this scheme, users are assigned queries in an offline phase. This allows a reduction in the communication cost, such that the user sends one bit. There is no addition of direct noise to hide the user's group. Instead, we leverage the randomness of the user's value in addition to smart queries. To gauge the performance of our scheme, we compare it to a scheme we call the randomized group. The randomized group scheme consists of each user reporting a noisy version of his group and value to the server. This is an extension of methods in the literature, mainly randomized response. Essentially, the user lies about his group with some probability. Then, the server cannot be certain about which group the user belongs to. To compare our Q&A scheme to the randomized group scheme, we fix the communication cost and look at the error versus privacy. This graph is for given user value distribution, P1 equal P2 equals 0.5. Here I remind you that P11 is the probability that the user has value 1 given that he belongs to group 1. We observe that the Q&A scheme, represented here in blue, outperforms the randomized group scheme in the high privacy regime. The high privacy regime is when the privacy parameter epsilon is small, and this is desirable because it ensures that the group is adequately hidden from the server. The key idea for why it outperforms is that in Q&A we send a compressed version of the information, so we are sending less bits per user, and because of that we can accommodate more users. More users imply in less error. This observation that the Q&A scheme outperforms in the high privacy regime is consistent for different user value distributions, and we find closed form expressions for all these curves over here. Finally, I wanted to point out that in our paper we generalized these results to any number of groups and alphabet size. Here I show our main theorem, and more details can be found in our paper. As for future work, we want to find theoretic bounds that characterize the best performance achievable for a given privacy and total communication cost. Thank you everyone for listening, and please feel free to contact me with any questions you might have.